So in our previous little lecture here, then we introduced kind of the idea of why we're even studying astronomy. So now let's go ahead and get started and talk a little bit about some of the things here. First chapter of the book. Okay, so chapter 1. Now, Physics 1403 is really the second half of your textbook. But I don't assume that you've had the other class, 1404 class, which is solar system, which is the first half of the book. So I don't assume you've had that ahead of time. So what I'm doing is I'm going to go back and cover some of the background stuff I expect you to know. And so chapter 1, kind of basic introductory stuff. And one of the things that we do in chapter 1 and 2 is introduce the idea of what is science, because this is a science class, and the scientific method. So in studying the scientific method, and again, right now we got all these issues out here with the virus and the pandemic, and a lot of people that don't know science are saying, hey, I know more than the experts do, and I saw this number and that makes sense and so forth. Well, that's not how science works. In science, you don't just look at something and say, I understand because I think that's how it ought to go. For example, Aristotle, very smart guy, but his idea of how things move was that he looked at it and said, I think it ought to work like this, therefore it does. And so he said, if you have an object, you throw it, then if you throw it, it moves in a straight line. So you throw it upwards, it moves in a straight line until it runs out of whatever you gave it as it's throwing, and then it drops vertically. And so you throw it, and it's like, okay, does that move? I mean, is that moving in a straight line? Well, no, it's not. Okay, Aristotle didn't care about that. He said, well, it seems like it ought to work that way, therefore it does, so you must be looking at it wrong. Okay, politicians think the same way today. In science, what we do is we start off and we say, okay, I have an idea how I think it ought to work. We don't just come up with an idea out of nowhere. The idea is based on an observation or a previous set of facts. So what you do is you say, okay, now, based on what we know, let me extend that and say, this is what I think it ought to be. Okay, this is how I think it ought to work. Then what you do is you test it. That can be an experiment. You do something or you observe something. I think it moves in a straight line, so you throw it and see does it move in a straight line. If it does, your hypothesis may or may not be right. It could be something else that make it go in a straight line. If it doesn't, your hypothesis is obviously wrong. So what you do is you disprove a hypothesis. That's your experiment. In some cases, you can't actually just go out and say, hey, I do an experiment. You can't say, you can't say, this is my ideas how stars form. You can't go create a star in the laboratory and see how stars form. Okay, but what you can do is you can look out into the galaxy where stars are forming and see if they're forming in that fashion. Okay, your hypothesis must be testable. That means you have an idea as to how things work. There has to be some kind of observation or test to be able to verify it. You might not have to actually see it happening, but you ought to say, hey, if it does this, then that should be the result, and you go and look and see, are things that way? And so that would be a test. Okay. Now, if you've had a hypothesis, and the hypothesis was based on an idea, okay, and that idea has this hypothesis, you flesh out the idea, it has several other hypotheses. If all these hypotheses are confirmed by experiment, then that means you can create a model. Okay, a model is a mathematical description of things. This would be like the Bohr model of the atom. It says, that mathematically we can describe an atom as a nucleus with electrons going around it. Now, that's not exactly how atoms are. Definitely not how atoms are, but it's a model, a mathematical description that if you go through the math, it says that you should have certain energies, you should have certain kind of things happening in the atom, and in fact, that's very close to the way atoms behave, so even though that's not the way the atom really is, it is a good model for an atom. Okay. Related to that is a theory. A theory is not just a hypothesis. Common use of the words are, okay, a theory is going to be like an idea. No, a hypothesis is your idea. A theory is a set of mathematical descriptions and models that have been verified. So the theory of gravity doesn't mean I think there's gravity. The theory of gravity is the description as to how gravity works. Okay. And so that's the idea. So this is the basics of science and the scientific method. Astronomy is a science. It's not just, a couple guys going out and saying, hey, I look out there this way, I think it is. Okay. No, it's stuff that's been verified. Okay. Through observation, experimentation, models, and theories, mathematics. So your hypothesis can be empirical. That means it's based on observation or experience. Hey, I noticed that when I drop something, it falls down. So that means I'm going to have a hypothesis that every time I drop something, it falls downwards. Deductive. That means my pre-existing theoretical work was that gravity attracts things. Earth has more gravity than other things, so I drop things, it goes towards the Earth. Okay, and it should fit with previous work, so you don't just, have an idea that doesn't relate to anything. You have to have it relate to what has already been verified in the past. Now, hey, you drop a helium balloon and it goes upwards, okay, that doesn't seem to fit. Well, that means you have to modify your original ideas and say, well, why does it drop? Well, it drops because gravity pulls on it. There's other forces acting on it. Buoyancy of the air. Well, if the buoyancy of the air, the upward force is bigger than the downward force of gravity, it's going to go up. And so that's how things rise. So that means you have to add it on into other ideas. The idea of gravity, the idea of buoyancy. Okay. And you have to be testable. If your hypothesis cannot be tested, it's not really scientific. So you say, well, I think it's this way because, and then there's no way of testing that, then that's not really a scientific hypothesis. That's just an idea you got. SI units. SI stands for the French for International System. I don't actually try to pronounce that in French because it really freaks out anybody that speaks French. But the SI system, your book goes through this in chapter 1. Kilo means 1,000, so that's 10 to the third. Okay, I'm not going to really write, this always like that, but I will reference this. So I might write 10 to the 9, something times 10 to the 9. That's going to be giga. So rather than giga years, which means billions or billions of years, so I might say, okay, instead of saying that the universe is 14.7 giga years, and instead of saying 14.7 billion, it's a lot easier to write 14.7 times 10 to the 9. Okay, nano, that's a very small sort of thing. That's going to be like a nanometer, or which is like 1/1000th of a meter, or times 10 to the minus 9. And so you ought to learn how to enter that into the calculator. There's typically a button on the calculator for using scientific notation. If you use that button, that's easier than trying to enter a number and then multiply and then 10 raised to a power. If you just enter something, hit button, and then the exponent, that tells the calculator that's all one number. If you don't enter it that way, then your calculations are going to be off sometimes because the calculator won't know what you're trying to do. So I would say go ahead and look up the instructions for how to use your calculator. All right. So background stuff. Class is called Stars and Galaxies. So let's talk about stars. You go out at night and you look up in the sky and you see stars. So there's stars in all different directions around the Earth. Theoretically, depending on who you ask, depending how good your sky is, depending how good your eyes are, etc., there's roughly about 6,000 visible stars in the sky. Now, on the other hand, if you go out at night and look up, you don't see 6,000 stars. So why don't you see 6,000 stars? Well, there's a variety of reasons for that. Part of it depends on how bright your skies are. Part of it depends on how good your eyes are. Part of it depends on where you are. Okay, trees, buildings, things get in the way. Now, the other thing is Earth gets in the way, because that's 6,000 stars in the entire sky. So you can imagine out here in space somewhere you have Earth, okay, and then you look off into space, and if you're on one side of the Earth, you only see the stars on that part of the Earth. The stars on the other side of the Earth you don't even see, and so you can only see half of that any one time, and so there's a variety of factors that play into this. So that's why you don't see 6,000 stars. In fact, this is going to be one of your lab exercises, is go out at night, 3 nights, over the next month or so, and look up and count how many stars you see, and then explain why you only saw the number of stars that you see. And in fact, what you might do is you might look at the stars from one location, and on some days you see more, and some days you see less. You might look at stars from one place one night and another place another night, and you might see different number of stars. Okay, why? Well, explain that. So that's what the lab is going to have you do. That's one thing. The next thing we'll be talking about is constellations. And so I'll save that for our next little short video lecture.